Today we will be doing microprocessors. Now, we will not be writing microprocessors again and again because it's a very long word. What you can do is, you can use this simple, this is micro and this is P, that stands for processor. So whenever I say microprocessor, you can just write this thing for your understanding. And if I say microcontroller, so you can write like this, micro and controller, right? So guys, the very first thing that I would like to ask you, we'll start with the question. What is the voltage that comes at our homes? 220 volts. And on the first day, we told you that how many amperes are coming at your home? You can detect it from the meter, from the meter that is given to you by your electricity department. Now, can you tell me at how many volt does a computer work? At how many volt does a computer work? 5? How many say 5? 5 volt? 10? 12? 110? 220? 220? There are a lot of guys who are not actually saying anything. So let me tell you guys, every microprocessor works on 5 volts. How many volts? 5 volts. So as we told in the starting, that diode is needed, a capacitor is needed to make a rectifier and a step down transformer, obviously. So all these things are needed to step down the voltage. That is called the power supply unit of your computer. You have heard that power supply kharab ho gayi. Power supply is not working. What is that power supply? Power supply is a simple device that steps down the voltage, rectifies it, and gives 5 volt DC. 5 volt DC. Now, another question to you is, why does it work on 5 volts? Why not at 1 volt? Why not at 220 volt? Why are we putting a power supply? Why are we not using it at 220 volts? Any guesses? Huh? That's what I'm asking. Why DC and why only 5 volts? Huh? For? Can you speak it louder so that everyone can hear it? You're right. You're right. So he's saying for biasing. Now, microprocessor consists of transistors. We were learning transistor from the first day in the last lecture, and till now we are talking about transistors. Now, transistor is a very important component when we are talking of computers, robotics, calculators, from very simple device going to a very complex device like a robot. Transistor is that device that enables us to do digital computing. Now, we have learned that transistor is a semiconductor device. Am I right? Transistor is a semiconductor device. Now, what do you mean by semiconductor? What do you guys mean by semiconductor? Now, semiconductor device, as we told you on the first day, it sometimes lets the current pass, let the electrons pass, and sometimes at certain circumstances it stops the current. If we change the circumstances at which we are providing the current, at which these 3 legs of the transistors are, then we can manipulate whether it will pass or stop. Am I right? Am I correct? This is what we studied. That is a semiconductor device, right? So at certain circumstances it will either pass or stop the flow of current. Now, because of that, we are still using binary system, because a transistor would either, it will pass the current 1 or will stop the current 0. So this two binary number system, binary means 2, right? Binary means 2. That's why this system came into existence, because the transistor can either let the current pass or it will stop the current. So 0 and 1. Now this 0 and 1 system has led to a lot of different advancements. This binary number system, it is very difficult for humans to actually understand or calculate, but for computers it is very easy, because they are using transistors. At certain circumstances, if we apply the gates, we have not studied the gates right now because we were not able to complete our project as of for now. After this we study the gates, but until unless you complete this project, you will not be understanding the gates. So that's why in the last lecture we will be studying all these different things. Please settle down. So the transistor can be fitted by different methods to make different gates. Now these gates can be AND, or, I'm so sorry, whenever we write gates, we always use capital letters. These are the basic 3 gates that we are using in any computer system. Basic. There are other gates also. XOR and NOT, NAND. So I should consider that you know all these gates. So we can skip this topic. Can we? Great. You saved a lot of time. So let's skip this topic of gates and again come back to what we call as microprocessors. Now we are starting from the very beginning. That's why you would think sometimes that what exactly am I telling you? But slowly and steadily we will be moving on to the microprocessors. Now as I told you, there are different gates that gives us the freedom of doing different computations, right? But you saw that the transistor was this much big approximately. How much big? This much big. It was small, was it? It was small. Transistor was a small thing, right? But do you know how many transistors are there in your computer or your laptop? How many transistors are there in a robot or your computer or your laptop? Can you tell me? Millions of them. Millions of them. Now, how do we fit all these transistors in that simple computer or a simple robot? How? Now, this technique came in early 1980s, or we should say 1978 or something like that. Let's not go deep into history. This technique came in which we can actually integrate these circuits at a very small level. We can integrate these circuits at a very small level. And after integrating it, what did we got? We got a microprocessor. We got a microprocessor. Now, microprocessor is having thousands to millions to billions of transistors in them. The more the transistor, the better the better the processor is. I will tell you how. The basic thing is actually clock. What is the clock speed? But I'll make you understand all those things later on in an hour or so. So the bigger, the more the transistors in microprocessor, the better the microprocessor can work, because the amount of work it can do is more. The amount of work it can do, because as I told you, transistor act as, if we use transistor, then we can make gates. It can either it can either allow the current to pass or stop it. And that will mean either the result is positive or a true or a false. Correct? This is the basic funda behind that. So this microprocessor came into existence, which has a lot of circuitry in them. And now we are moving forward to the basic architecture of microprocessor. But before that, just one thing which we are left with is what is the difference between microprocessor and a microcontroller. You should know it. It is very, very important. What is the difference between a microprocessor and a microcontroller?
Microcontroller is a single specific.
Now, if we talk about a microprocessor, let's talk about microprocessor. Right? This is a microprocessor. Now, to give input to a microprocessor, we need a chip which provides the input. IP means input. Right? There's an input output chip that can actually handle the input and output. There's a special device that is called a timer. And at the end, we need memory. What we need? Because whatever we are doing, we have to store it somewhere or the other. We need to store that thing. Whatever computation we are doing, we need to store that computation in some place or the other. So we need memory. Timers, there are different devices that use timing circuits. For that we use timers. And obviously, we have to give inputs to the microprocessor so that it can work. Correct? So that's why all these different things are important for a microprocessor to work. If we don't use these things, then it would be very difficult for us to make a microprocessor do any work. But after some time, scientists came with a device called microcontroller. Now what they did is, they did something very fancy. What they did was, they took one single chip, and integrated everything in it. Integrated every single thing inside it. And this chip was called microcontroller. This whole thing that is inside a box, inside a single chip, is called microcontroller. I need feedback from you guys, otherwise this class would become boring. What is this called? Microcontroller. And what is microprocessor? It is only the processing unit. It is the brain. It is that brain that tells you what exactly you want to do. But for that brain to work, we need eyes, we need ears, we need our hand to give the output, or to time the circuit, or to store the things. We need all these things. But microcontroller is whole body. It doesn't need anything else. Microcontroller does not need anything else. Are you sleepy? Go and wash your face once. So microprocessor is the brain, whereas microcontroller is the whole unit. Microcontroller does not need any other chips or any other circuitry to make it work. We can directly give the signals to it and make it do our work according to us. Got the difference between microcontroller and microprocessor? Now let's come on to the benefits of microprocessors and the benefits of microcontrollers. If we talk about microprocessor, because it's a different unit, we can change the amount of memory in that. Can we? We can change the amount of memory in that. We can change the timers that we want to. We can change the type of input that we are giving to it. Correct? Am I correct? So this is highly configurable. It can be made to do the work on your demands. But at the same time, it is more costly because it is having a lot of things in it. You have to attach a lot of device to make it work. But it is highly configurable. Whatever thing that you want it to do, it can do all those different things. Now coming on to the profits, the benefits of microcontroller is that it is very small, it is lightweight, and it is cheap. Fairly cheap enough to microprocessor. Why cheap? Because the processing power is generally less than microprocessor. Microcontrollers processing power is generally less than microprocessors. Why? Because in that single chip, you are integrating everything. So the amount of circuitry in that, we have to reduce for the computation and increase for the other devices and the memories. Correct? So it will take more, it will definitely take less space, but the processing power would decrease. Now what do you think? Which one is better for a robot? Microcontroller? Why? Processor? No one is wrong. If someone says microcontroller or if someone says microprocessor, no one is wrong. Because if we are making a very advanced humanoid robot or a very advanced robot, then we will be using microprocessor because it's very large. Right? Because it's very large and we can put a lot of different things and it doesn't matter what the weight is, what the power it is using, doesn't matter. But if we want to make a small robot or the robot that I made, in this much chip, we have to integrate every single control in that. Input, output also, the power also, the registers, the memory, everything inside that. So for small robotics, we use microcontrollers because we do not need a lot of processing power. Do we? Do we use? Not a lot of it, a bit of it. But again, when we are working with microcontrollers, we are limited with the number of sensors that we are using. So with every single microcontroller that you purchase from the market, there would be a list of the devices that you can pair with it. After that, you never know whether it will connect or not. You have to see the data sheet of that sensor or something like that. That what kind of feedback does it provide. So that is the positive and the negative of microcontroller. Microprocessors are expensive. These are put up in your computers generally. You are having a video card, right? If we are not talking about laptops right now. Let's talk about your old desktops. They would be having a video card in that, right? And you said, oh, I have got 1 GB of this, I don't know, what is it called, video card or something? Graphic card, I'm sorry. And I do very good gamings over that, right? Used to say that when you were in school? So, and you can change the amount of RAM in that, right? Memory. You can change the amount of storage in that, the hard disk. You can put up a CD drive or a DVD drive or a Blu-ray drive or anything, input devices. You can plug in different kinds of printers. You can plug in different kind of plotters. If you want to modify it, you can modify it. Because it is having micro. What does it have? Micro. Right. And microcontroller is used in small robots. There are robots that are changing from microcontroller and switching it over to microprocessor. So now you know what is the difference between microprocessor and a microcontroller, right? Now, this is one difference that is difference between microprocessor and a microcontroller. After that, we'll be knowing a difference between, because these things are very elementary things and anyone can ask you these things when you have done this workshop, and I don't want you to be confused in that. Now, there are two types of systems. One is embedded system. One is embedded systems and another is microprocessor system. right? What are the two types of systems? Right? Now, in these two types of systems, what is the difference? Again, what is the difference? The difference is that microcontrollers or microprocessors, because you know, when we are talking about microcontroller or microprocessor, the brain is the same, the processing power and the speed decreases. That's the only difference, right? So if we talk about microcontroller or microprocessor, they can be again and again reprogrammed. They can be again and again, what can it be done? Reprogrammed. I need the sound from your side also, guys, right? It can be reprogrammed so that I understand that yes, you are understanding each and everything. If you just sit in front of me and you don't say anything, I would get to know that okay, you are just, I'm teaching scarecrows. So we are talking about embedded systems and microprocessor or microcontroller systems. Now embedded systems are there in your calculators. I'm not talking about your what you call scientific calculators. I'm not talking about that. I'm talking about that orbit wala calculator or something like that. Those simple calculators that you have at shops and all. So can you change the programming of the system inside that? It is hardwired. It cannot be changed. Once it is programmed at the company, it cannot be changed. If we talk about a toy, any toy, a remote control toy, can you change the programming in that? No. Again, embedded systems. So in embedded systems, once programmed, done. Your microwave oven, your TVs, your fridge, your microwave, all these are having which systems? Embedded systems. Now the profit in that is it cannot get virus. It is not easy to damage that software that is in that. That program in that, I should not say software, a program in that. And it can be ensured to work for a very long duration. It doesn't damage very easily because the data in that is permanent. It cannot be erased. It cannot be erased. It cannot be reprogrammed. So you can be sure that okay, whatever I am giving, it's done and finished. Nothing can be changed in that. But again, we come to the negative sides of that. Now the negative sides of embedded systems are, do you think you can use it in robotics? Can you? No, because we need to make constant changes. We need to learn things. If we are making a robot work like this, then especially in humanoid robots, the robots that I am researching at, 99.9% of the people on this earth who are working with the humanoid robots cannot make him walk in just one go. Never. Whether you take a person from MIT, Stanford, Harvard, anywhere in this world, no one can program a humanoid robot to just a new robot, I should say. That we just made a robot and we said, okay, this is how it should work, and we programmed it and it was like, okay, that's great, perfect. Because walking is a very difficult task. Or any other robotic task that we say, you have to make changes according to the environment. So the embedded systems are lagging behind. So the embedded systems are hardly used in robotics, hardly. Because they cannot be reprogrammed. That's why we use microcontroller or microprocessor systems. Got it? So what is the difference between microprocessor and embedded systems? Cannot be? Cannot be? Great. And microprocessor or microcontroller systems can be? Perfect. Now, moving on, I'll be drawing this kind of diagrams while I'm teaching you. Let me make it a bit more thick so that you get this very clear. Did you saw this kind of diagram when you were drawing the diagram that I gave you, the architecture? This kind of lines were there? Did you saw it? It was there. Now, what does this indicate? Does anybody know? It indicates bus. What it indicates? Bus. Now what is the meaning of bus? The bus that you go home in? Or anything else? Huh? Cables? So bus is, if we talk about a bus, it is a set of lines. It is a set of lines. It can be timed or asynchronous. This means asynchronous. You can also write it synchronous or asynchronous according to your convenience. Synchronous or asynchronous. I'll tell you what does that mean, but as if for now, what you have to learn is that, let's say we took 8 wires and the data is flowing in that. We took 8 wires and the data is flowing in that. So we can, at a specific point of time, we can send a lot of data as compared to a single wire. Correct? We can actually send a lot of data at a single moment of time. So the speed of that system would increase by 8 times. If there are 16 wires, then how many times? 16 times, 32 times. As if for now, you need to know this. After that, I'll be telling you in deeper knowledge that what exactly these bus are. Now, whenever we will be drawing this kind of symbol, then you don't need to draw it like this. You can just simply draw like this, and you can write. I'll be telling you that how many bits is it carrying. How many bits is it carrying? Whether it's 8-bit, so you'll write 8-bit, so that you know that it is 8-bit. Or if I say 16-bit, then you'll write 16-bit. Do mention whenever I say that how many bits are being carried by this bus, because it's very important. Now moving forward, now what right now I'm teaching was the preliminary knowledge of the microprocessors. Now we'll be jumping deep into this ocean of microprocessor, and you need to be very attentive for next 1 hour to understand all the things that I'm going to tell you right now. Fine, guys? So, and keep drawing whatever I'm drawing right now, right? Keep drawing it. Now, there's a circuit in microprocessor. We'll be using the term microprocessor as of for now. We'll not be using microcontroller. We'll be just using microprocessor because we would be studying 8085 microprocessor. What will we be studying? 8085 microprocessor. And why am I making you study all these things? Is because the next time I'll be coming with a microcontroller that looks like this. That looks like this. This is an Arduino. A lot of you guys have heard of it. Have you? Arduino? You have heard of it? So this is the very basic microcontroller that is used to program robots. Very basic. Go to Google, write this name, Arduino, Arduino. Arduino. There is Arduino Uno board. Arduino Uno board. And search on YouTube also that what kind of projects are the international students doing by this board. You will be amazed to see the projects that they are doing. They have made a flying ball that automatically balances according to magnetic field. They have made a sensing mouse. You just fit a small gyroscope out there that's very small, and you move your finger and the mouse actually acts the way you want it to be. You click it like this, the icon clicks. If you do like this, the page swaps. So this is something they have made by the simple microcontroller, and this is very cheap. If we talk about the MRP, it is an Italian board. It is made in Italy, and it is costing somewhere around 1,500 to 2,000 rupees. But when we just ship it to India, we give the duties, we give the taxes, it becomes somewhere around 5,000 to 6,000. So we'll be giving you these kits next time. But as of for now, because it is having a microcontroller that you can see out here. Can you see it? Can you see it? So this is the microcontroller over here. So when I teach you this microprocessor, then you will be able to understand all the data sheets of other microprocessors. Maybe some intelligent guys would also be able to learn, able to understand the data sheet of microcontroller also. No doubt it's difficult. So now, moving on, what I'll be starting with would be architecture. So just keep drawing whatever I'm telling you. Whenever we are talking about a microprocessor or a microcontroller or anything, what is the basic thing that is needed for it to work? The basic thing. What is the basic work of a microprocessor? Input? Take the input process. Process, what do you mean by process? Manipulate. Now, what are the different kind of manipulation that you do? What are the different kind of manipulation that you do? Arithmetic and logical, right? Arithmetic and logical. And there are some inside functions like copy, paste, move from here, move the file from this place to another file. These are the operations that a microcontroller or a microprocessor has to do. So we'll be concentrating basically first on this diagram. What is it doing? Draw it as I draw. Why am I making it clean? Because it can be sometimes confusing for you. Execute, E-X-E. I don't know what is happening to this pen. Execute, this is execute. Fetch and execute. Everyone has copied this diagram? Everyone? This is a very important diagram to understand how a microprocessor works. Instruction cycle, fetch, execute, machine cycle, states. Very easy diagram, but a very, very, very important diagram. Now, let me give you an example. Don't look out there. Don't look out there. Look at me. Whenever you need to do some work, let's say you have to go to college. You have to go to college, or VIT, I should say. So, do you directly jump into college, or are there certain steps that you follow before coming to college? There are certain steps, and can someone tell me what are those steps if they are not too personal? Yeah? Okay, ID card. Yeah, that's most important. Except for that. Do you brush your teeth? No. Okay. Okay. You brush your teeth. Yeah, that's important. Then you take shower. You put on clothes. Then you put your feet in slipper or tie up the shoes, and then walk towards the college. That's how we generally think it goes forward, right? Right? This is how we think it goes forward. But the basic funda is that you directly just don't jump into college. Out of nowhere, you cannot jump into college. Yeah, I'm present. Right? So everything in this world, whenever it happens, so there are different steps that it follows when that particular task happens. There is a specific algorithm, there is a specific sequence in which that task happens. Correct? Is this right? So that sequence, we have to see what sequence does a microprocessor follows. Now, these are all the subsets of instruction cycle, right? So when you talk of instruction cycle, then let's say I gave you the instruction to come to college, right? That is the instruction that has been given to you that, hey guy, hey brother, you have to come to college, right? This is called an instruction. But there's an instruction, when it is given to you, then the instruction should be fetched to you, should be told to you. When you hear that instruction, then you have to execute that instruction. Correct? First of all, you have to hear it. You have to get the perception that, okay, I have to go to college. Today is Sunday, but I have to go to college. Danish would have told you that, okay, the class would be from 10 to blah, 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 whatever. So he has fetched that information to you by a certain channel. Correct? And then you have taken the steps to execute it. Correct? Now, again, this is not the smallest quantified unit. We can again still break it into parts. He might have thought something. Danish is present? Okay, good. Let me take his example now. So he would have taken he would have thought something in his mind. He have thought of the timing. Then he would have thought what to say, and then he would have said it to you. Right? So there are different steps that are involved when he is doing different things. Let's say thinking. This is thinking. This part is thinking. This part is organizing what to say, what exactly he has to say, and this is telling it to you. Right? Let's say these are the three basic steps of how he would tell you what is the timing of the class. Right? But again, when he is thinking something or he is telling it to you, then he will tell you where to come, when to come, how to come. Right? Where to come, when to come, or how to come. So this is one more smaller division of that cycle. So that thinking, when we are thinking something, We are then organizing something. Please switch off Sir's mobile. So when we are thinking something, or we are organizing something, or we are saying something, that is called machine cycle. Machine cycle means whenever, I'll tell you what it means after some time, but let's first go down to states. Let's first go down to states. What exactly are states? Now, as I told you, whenever he will tell you that where to come, how to come, when to come, or anything else that he wants to tell you, that is the minimum thing he can do. Anything beyond that, anything smaller than that. So this is called states. When we tell a robot that, hey, Mr. Robot, you have to do this thing. That is called an instruction. What is it called? An instruction. An instruction has been given to the microprocessor. But how is it given? First, the instruction has to be fetched. The instruction has to be given by some channel to the microprocessor so that the microprocessor can understand what to do. Right? A microprocessor should understand what exactly he has to do right now. Once it understands what he has to do right now, then he can proceed forward to execute it. Right? But now, when the instruction has to be fetched, let's say the instruction, the fetch cycle, this fetch cycle has different machine cycle, in which machine would do different types of work. When we will be giving the data, to the microprocessor or the microcontroller of the robot, then what will we do? We'll first load the data, then we'll say, okay, now store the data, now decode the data. Right? Now, I should not say decode the data in fetch, because fetch does not allow to decode the data. That would be in execute. So we can say that, okay, the data has been given. There can be two machine cycle in fetch mode, or there can be 5, or there can be 10, there can be 15, there can be 20, depending on the types of systems that we are having, depending on how the architecture has been made to work. Right? You can complete your paper in 2 pages or in 100 pages. That's upon you. Right? The end result is completing that paper, completing that exam. Right? A person might take 5 minutes to take a shower or an hour to take a shower. Right? So that is upon the architecture of the microprocessor, how it actually works. That how many machine cycles are needed in that. When we talk of giving the data, then what happens is the data has to be put on the channel. Then the microprocessor has to be told that, okay, the data is present on the channel, please catch it. If you throw a ball to a person, you'll say, hey, catch. Right? I would not hit him directly. He'll say, man, what are you doing? Right? So when I'm going to make him catch something, then I'll say, hey, catch. Then I'll throw it. But the microprocessor does it in a different way. It puts the data, then it says, hey, catch. Right? Because microprocessor is faster than you. So it can actually afford to do all these idiotic things sometimes. So what it does is, all the time, it puts the data on the bus. Where does it put the data? On the bus. And then it says, hey, I put in the data, collect it. I'll remove the data in this much time. Right? And after that, when it stores the data, it gets the acknowledgement, hey, I've got the data. Microprocessor says, okay, I've got the data. You're good to go, remove it. Then it gives a feedback that, okay, I've eaten the food, I'm done. Right? So it would give a feedback to the device, the memory or anything, that, okay, I've got this data and now you're good to go. We are done. Another state. So there are different states that are being used to do a simple task. as I told you, especially in computers, it has to do everything in an organized manner. It has to do everything in an organized manner. So the minimum work that a microprocessor can do is a single state work. It cannot do a half state work. Half state is nothing. Got it? Now you'll say, what exactly is a state? What exactly is a state? I have told you that, okay, it works on states. What is state? States can be directly related to clock. States can be directly related to clock. You say, my computer is of 3 gigahertz. It means that it can do 3 mega things, or let's say you say that, okay, my computer is of 10 hertz or 100 hertz. So it can work for 100 states in 1 second. If we say 1 kilohertz, how much? How much? We say 1 megahertz, then 10 raised to power 6. If we say 1 giga, then 1 raised to power 1 raised to power something. 1 raised to power 100 is nothing. 1. 10 raised to power 10 raised to power 1 answer. 9. Or 1 tera? 1 tera? 12? 1 tera? You made me confused. Okay. So in 1 second, it can do 10 raised to power 9 different activities in 1 second. Your microprocessor can do this much work in how much time? 1 second. Can you imagine how fast would that be? That is the fun of microprocessor. That's why it is called a very, very fast device. Right now, if someone says, hey, the 8085, it's a very slow microprocessor and it was developed in 1982 or 80 something, and why are you studying this? This is just 3 megahertz. 3 megahertz? 3 megahertz? Can you imagine how much that is? And when you are talking of, hey, I've got a 2.8 gigahertz, you have 2.1, it's slow. You can get to know the complexity of the situation, the complexity of the race that we are having in the speed right now. Right? So the clock, whatever you say, that okay, 2.4 gigahertz, 2.8 gigahertz, that is the clock speed. How much minimum amount of work it can do in 1 second. Isn't that a lot? Right? So, did you knew this earlier? Good. Now do you know it? Do you know it? Yes. Good. Now, this is clear? Is this whole diagram clear? Any doubts? Have you got everything that I have taught? Every single thing? Any doubts from this side? This side? Any doubts? Clear? Good to go? Great. So, this is actually the most important part of the microprocessor whenever we are studying. And if you know this thing, then working with microprocessor, especially when you read it from books or when you read it from the different data sheets, it would be much more easier because this kind of diagrams would be there in it. That how it works. I'll be showing it to you how it looks like, but after some time. Now, let's do this all. You have drawn it? Have you drawn it? All of you? Shall I delete it?